So it is my absolute pleasure to have Professor Ipsen here to speak to us today. She is a professor of mathematics at North Carolina State who specializes in numerical analysis and numerical linear algebra and is a leading expert in randomized algorithms, among other things, in those two areas. She is, in addition to her highly influential work, she is also on several editorial boards for numerous journals, including the SIAM Review, and is a fellow of both SIAM and AAAS. So I'm really delighted that she agreed to be our speaker today, and I'll turn things over to her to tell us about BayesCG.
Thank you so much, Mark. Thank you for the kind introduction, and thank you to the organizers for inviting me to talk here. So this is joint work with two statisticians, John Cockayne and Chris Oates from the UK, and Tim Reed, my graduate student at NC State. So what is probabilistic numerics? While probabilistic numerics seeks a statistical treatment of approximation errors in deterministic numerical methods. So what's happening is one assigns probability distributions to quantities of interest and then expresses these deterministic methods as probabilistic inference. And what we want to do is to model the uncertainty due to limited computational resources. So that's truncation errors in discretization, early termination of iterative methods, and so on. So given that there are all kinds of error bounds around, why would one want to do this? Why we want error estimates that are more informative than the traditional pessimistic bounds. And we also want error estimates that can be propagated through computational pipelines. From the perspective of the field of uncertainty quantification, our approach is an instance of model discrepancy with epistemic uncertainties. Okay, so let me just give you the high-level view. So we have a non-singular matrix A and the right-hand side B. We want to solve the linear system. We get a unique solution X star. An iterative solver starts with the user-specified initial guess X0 and then computes iterates that we hope converge to the solution X star. So what we are going to do is select a prior distribution which reflects the initial knowledge about the solution, which can be nothing. And then the solver computes posterior distributions that reflect the increasing knowledge about the solution after as the iterations progress. So I'm going to talk a little bit about the history of probabilistic numerics, justify the Gaussian probability distributions, talk about solving systems of linear equations, and then solutions with BayesCG, talk about choices of prior distributions for BayesCG, and then efficient low-rank Krylov posteriors, and end with a take-home message. Okay, so here's a little bit of history of probabilistic numerics. So probabilistic numerics is attributed to Henri Poincaré, who was the first to interpret computation as inference, in particular in the case of interpolation. Starting in the 1950s, Soldin and Larkin interpreted interpolation as in terms of Gaussian measures on Hilbert spaces. Then there's a seminal paper by Kimmeldorf and Warber, which interprets splines as posteriors of Gaussian processes. No, not as posteriors, as means of posteriors of Gaussian processes. Then Percy Diaconis coined the term Bayesian numerical analysis and applied the Bayesian approach to quadrature, and that was followed by Tony O'Hagan, who applied the Bayesian approach to quadrature optimization and interpolation. Okay, so that was work from last century. There has been quite a bit of work, last millennium actually, there's been quite a bit of work this millennium, starting with a paper by Andrew Stewart on conditioning and uncertainty quantification. Then there's the call to arms for probabilistic numerical methods by some of the key areas in this field. Then one paper that was really motivating for me is the probabilistic interpretation of linear solvers by Philip Hennig in the context of optimization. Then there's a paper by Cockayne, Oates, Sullivan, and Girolami, which tackles these probabilistic numerical methods in the setting of nonlinear, non-Gaussian distributions, and that is really very difficult. And then Chris Oates and Tim Sullivan give a really nice history of probabilistic numerics in their modern retrospective. Okay, there is probabilistic numerics has connections to many other areas: information-based complexity, average case analysis, data assimilation, and statistical learning. And again, I have to be always very careful. We are not doing uncertainty quantification. So I'm trying to get the differences clear here. In uncertainty quantification, the problems are usually ill-posed, and the uncertainties can arise from all kinds of sources: model uncertainties, parameters, experimental measurements, and so on. While here in probabilistic numerics, we have well-posed problems. And our uncertainty at this point is algorithmic due to limited computational resources. So there has been quite a bit of work recently on probabilistic numerical solvers. So here's a little bit. And the probabilistic numerics community has a web page that they just recently updated. And probabilistic numerics is applied to all kinds of other computations: optimization, quadrature, numerical solutions of ODEs and PDEs. And they also have a Git repository for putting code there, usually in Python. Okay, so the probability distributions we are going to look at are Gaussians. Now you could say, well, why Gaussians? Well, Gaussians are not analytically easy. So we are doing here a proof of concept. If we cannot deal with Gaussian distributions, then chances are we cannot deal with any distribution. So let's start with something that we have a chance at tackling. So Gaussian, just to review, it's a multivariate normal distribution. It's characterized by a mean vector x naught and a prior. The prior is symmetric, positive, semi-definite. If the prior also is positive definite, meaning non-singular, then we have a probability density function defined here in terms of an exponential. And this norm here is a weighted 2 norm, weighted by the inverse of the prior. The superscript T denotes the transpose. Okay, so why Gaussians? Okay, besides that they are easy. Well, linear transformations and conditioning preserve Gaussianity, which makes it easy for analysis, but also sampling is easy. So suppose you want to sample a random variable from a multivariate normal with mean mu and covariance sigma. You start out by sampling a vector from a standard Gaussian, and then you can shift and transform the vector to get your desired distribution. So here LL transpose is a factorization of sigma. So L can be the square root. It can be a Cholesky factor if sigma is non-singular. And if sigma is singular, which happens in our case, then it can be a thin Cholesky factor, where the number of columns is equal to the rank. And then in MATLAB, you just have a simple command to do this. Maybe I should apologize for using MATLAB, but I am an applied mathematician. And my students, of course, program in Python. Okay, so our purpose in life here is to solve systems of linear equations. So we've given a matrix A in the right-hand side. B here is our linear system that we want to solve. We assume that the matrix A is symmetric, positive, definite. Symmetric means that if you turn rows into columns, nothing changes. So turning rows into columns is accomplished by the transpose. Furthermore, the quadratic form in A is positive for all non-zero vectors x. That's what positive definite means. And of course, we have a unique solution. So positive definite system arise all over the place. Discretization of PDEs, covariance matrices in statistics, Hessians in optimization, polynomial regression, Gaussian process regression, all kinds of classifications in machine learning. So there's no shortage of symmetric positive definite systems. So what do you do if you have a symmetric positive definite systems? Well, you have two avenues. If your matrix is dense or has small dimension, dense means most elements of the matrix are non-zero. Small dimension here as well. On my 2015 laptop, I can solve linear systems with dimension 10 to the 5. So that is small, since I can do it on a fairly old laptop. So in this case, you use a direct method. If A has many zero elements, meaning it is sparse, or it has a large dimension, you use an iterative method. So let's just check the direct method. You do a Cholesky factorization. So you factor A into LL transpose. You can think of it sort of as computing a square root. And then you do two triangular solves to recover the solution. Okay, we are interested in iterative methods for solving these systems. And we view the gradient, the residual here, the difference between left and right-hand side of the linear system, we view that as the gradient of an optimization problem. Okay, so the function here is the objective function is this quadratic. So it's here, it's a quadratic in A, and then we have X transpose B. This is a convex function. Its gradient is the residual. So if the gradient is 0, then we have a solution, and this is the value of the objective function. However, usually we don't have the solution, we just have an approximation. So you can take the value of the objective function at the approximation, and you can subtract and add the value of the objective function at the solution. And then you can express this in terms of this quantity. It's a quadratic form, and xc minus x star, the transpose should be here, is the error in my iterate. So that means that the value of the objective function at an iterate is equal to the error squared plus some fixed value. So, and this error is weighted by the matrix under consideration. And this is a symmetric positive definite matrix, so this is a well-defined norm. So that means that the error measured in the A norm is a natural error measurement for symmetric positive definite linear systems. So that's why we are measuring the error in the A norm, because it just falls out here. Okay, so the easiest method for solving linear systems iteratively is steepest descent. So we follow the direction of the negative gradient. We start with the initial guess that's user specified, and then compute the next iterate. So this is here's an exact line search. And then one can show global convergence. So that means the error in the kth iterate is related to the error in the initial iterate by this factor that decreases and is less than 1. So that means this factor decreases, and here's k over 2, k being the iteration number. So this quantity, here's the condition number. What's the condition number? It's the 2 norm of the matrix times the 2 norm of the inverse. What does that tell us? Well, the 2 norm of the matrix tells us if the matrix is applied to a unit norm vector, how much the matrix can stretch that unit norm vector. The norm of the inverse says how much a matrix can shrink a unit norm vector. So the geometric interpretation of a matrix is often as an ellipse. So that gives the two extreme actions of the matrix, maximal stretching and maximal shrinkage. And that is the condition number here. So the convergence is fast only if the condition number is really close to 1, meaning never mind the directions, the matrix sort of does the same thing. So convergence is slow unless you have an extremely well-conditioned matrix, and really deep down, that is because we are maximizing only over, or minimizing over, a one-dimensional subspace. So that is very little. So that's why convergence is slow from a geometric point of view. Now, conjugate gradient goes a step further. So again, we start with the user-specified initial guess. We subtract it, we incorporate in the left and the right-hand side of the linear system. So here's the initial residual now, that's our new right-hand side. And then we are going to minimize at iteration k over a k-dimensional space. So as the iterations increase, the space over which we are minimizing becomes larger and larger. And the space is called a Krylov space. It's the initial residual multiplied by powers of a. So in iteration k, we multiply, so this is the R0 is the 0th power of a. That's why this superscript here goes only to k minus 1, that power. And you can see that the Krylov spaces are nested. So Krylov spaces from earlier iterations are containing Krylov spaces from later iterations. And the iterates are chosen so that the residual at an iteration is orthogonal to the Krylov space. So that means since the Krylov spaces increase in dimension, at some point that residual has no choice but to be 0, because we've exhausted the dimension of the ambient space, in exact arithmetic at least. So there is, that just means that the conjugate gradient method terminates in exact arithmetic. And we have global convergence, meaning we relate the error in iteration k to the initial error via this factor that now has the square root of the condition number in it, and it has a power k here instead of k over 2. And Philip Henning in his paper in 2015 in the SIME optimization journal gave a really nice interpretation of conjugate gradient in the context of quasi-Newton methods. And that's what really started it for us. This probabilistic numeric interpretation of linear solvers, in particular conjugate gradient. So in practice, of course, one doesn't have these errors, right? If one had the error, one would have the exact solution, then one would be done. So what we do in practice is, this is the error we want. It's a relative error. So the difference between iterate and solution divided by norm of the iterate, it's relative because we are operating in floating point arithmetic, and floating point arithmetic is defined by relative errors. And the general purpose error bound, they're much tighter ones, but the general purpose one is to bound the error above by the condition number times the relative residual, the backward error. So the relative residual, this is something we can measure, which is the difference between the left and the right hand side. The condition number, well, all we need is a fast condition number estimator. We don't need the condition number to 16 digits. All we need to know is the condition number 10 to the 8, 10 to the 7, or 10, or 1. So it's the residual that we can control. So the condition number, that is given by the problem, by our linear system. There's nothing we can do about it. The only thing that we can wiggle is this residual. So, and that indicates the numerical stability, the accuracy of the solver. And what one does in iterative methods, they iterate, but we don't iterate to completion because that takes too long. We stop once the residual is sufficiently small. It's less than a user-specified tolerance eta. Often people choose 10 to the minus 8, the square root of machine epsilon. A numerically stable solver in IEEE arithmetic should be able to get this residual down to 10 to the minus 16. Okay, so our approach now is to replace error bounds by probability distributions. So on what do we place the distribution? Well, there's matrix-based inference, which originated with Philip Henning, where one places a distribution on the matrix inverse. However, that is unwieldy and not easy to deal with. We are doing solution-based inference, where we are placing the probability distribution on the solution vector. So we don't need Kronecker products and tensor analysis. So the user gives a prior distribution that reflects the initial knowledge about the solution, which can be nothing. And then the solver computes it in iteration after iteration, posterior distributions. And that should reflect, those should reflect the knowledge, hopefully the increasing knowledge after more and more iterations. Our goal is to give an accurate error estimation for a single solve. And then the next goal is to propagate the error through computational pipelines, through successive computations. Because if you just, take this error bound here, and you give that to, say, PDE constraint optimization problem, the problem can't do anything with that error bound. So we have to have something that is more user-friendly for subsequent computations. Okay, so now here we come with our BayesCG solver, which is trying to do this. So let me again, we have a symmetric positive definite matrix. We want to solve this linear system. A user-specified initial guess is incorporated in both sides of our linear system. We compute iterates, which we hope converge to the solution. We are doing solution-based inference, so we are going to place a probability distribution over the solution. And the way we cook things up is that the approximations to the solution are at the same time the means of the probability distribution. We don't have to do that, but it's just so much easier. So the user has to come up with a prior. I will talk about how to come up with a prior. And then the solver computes posteriors. So we use Gaussian priors and then we compute Gaussian posteriors. Okay, so how do we do that? Okay, so suppose we have a user-specified prior, a Gaussian prior. What the solver does is the solver computes search directions. Say we are in iteration K, we have K search directions here, and they're linearly independent. If they are not, then the computation would have been terminated because we would have found the solution. Then we condition on the search directions acting on the matrix. Cocaine, O'Sullivan, and Girolami have shown that then there exists a unique Bayesian method that outputs the posterior. And the mean of the posterior is this highly unpleasant expression. The posterior covariance is this highly unpleasant expression. So you really don't want to look at it, but what you see is there is an inverse here. Okay, that inverse exists under good circumstances, but we really do not want that inverse. So what we are going to do is we are going to ask the search direction to be A sigma naught A orthonormal, meaning this whole thing collapses to the identity. So we do not have to deal with that inverse because we choose the search direction so that at every iteration, this is an identity matrix. So we remove a whole bunch of unpleasant work. And that gives us the Bayesian conjugate gradient method. So I don't want you to read the code, but what I have in here are red snippets. And these red snippets show the difference to conjugate gradient. So conjugate gradient is the black expressions, and Bayesian conjugate gradient is conjugate gradient augmented by the red expressions. And the red expressions occur when we deal with search directions as k and when we compute the posterior covariance. So BayesCG looks very similar to the conjugate gradient method. It's just a few statements that are different. And that's also how we implement it. So what are the properties of this Bayesian conjugate gradient method? There is a Krylov space. It looks a little fancier because we have a prior involved and the matrix occurs twice, but it's a Krylov space. If our prior is non-singular, then the kth iterate minimizes the error over this Krylov space in the norm given weighted by the inverse prior. So it's a very similar result to conjugate gradient, error minimization. However, often our priors are singular. And if we have a singular prior, but the initial error is in the range, in the support of that prior, we still have an iterate that minimizes in a pseudonorm. And if this condition is true, then this pseudonorm is non-zero. So it's a genuine minimization. And again, if we have a non-singular prior, we get a convergence bound very similar to that of conjugate gradient. So it's really comforting that our method reduces to conjugate gradient because conjugate gradient is really well researched and a lot is known about it. So that is really comforting. So let me just make a little local summary here. So we are solving symmetric positive definite systems. We came up with BayesCG, which is a probabilistic extension of conjugate gradient method. And what we want to do is we want to get a handle on the error in the solution or in the iterates due to early termination of conjugate gradient, because in practice, one cannot afford to iterate to completion. As an input, we need a Gaussian prior, and that models the uncertainty about the solution. And the mean of this prior is equal to the initial approximation to the solution. And then the solver goes, BayesCG goes iteration after iteration and produces posteriors, Gaussian posteriors. And the mean of the posterior is at the same time the iterate that tries to approximate the solution. And now, of course, the big question is, well, how do you pick that prior? Okay, let's look at priors. Okay, you could just throw up your hands in the air and say, well, let me just pick it as the identity. I have no clue how to pick it. Okay, that is not very effective. You could say, well, let me pick as the prior the inverse of the matrix. If you do that, then BayesCG reduces to conjugate gradient. So that means we can view conjugate gradient as Bayesian inference with a prior whose with a prior whose covariance is the inverse of the matrix. Of course, that's highly impractical, right? But on paper, we can do that. Well, there's also the so-called natural prior, a squared inverse, which converges in one iteration. Again, a highly academic prior, but on paper, it's fine. There's the preconditional prior, which tries to approximate this one, but being much cheaper. There's our new Krylov prior, which I will talk about, where these columns here are the basis for the Krylov space, and then you can cook up hierarchical priors. So the two priors that reproduce conjugate gradient are the inverse prior and the Krylov prior. And of course, these two priors have all the information in them that you need to solve the linear system. So once you have the prior, you have solved the linear system. So it doesn't make sense in practice. So these are impractical priors, but we have to look at their properties in order to come up with low rank priors that are efficient to compute. So that's what we're going to do. We'll investigate these, the Krylov prior in order to find a better low rank prior that is efficient. Okay, so we can get 2 times of error estimates from our distributions, pointwise ones, and then the ones from the covariance. So, and we are going to use a result from Gaussian quadratics. So if we have a random vector that's distributed as a Gaussian, and we have a positive definite, symmetric positive definite matrix A, then the distance of this variable from its mean in the squared A norm in expectation is equal to the trace of A times the covariance. And that is a result that follows just from a paper or from a result on Gaussian quadratics. So that means the convergence of the posterior means is indicated by the A norm error. So, and this is the approximation xk, and it's the traditional error. That's the pointwise error. The convergence of the posterior covariances can be captured in a trace. And the trace says, well, if our solution were so happen to be distributed as the posterior, then in expectation, our error would be given by the trace function that's a function of the covariance, of the posterior covariance. Okay, so now let's look what happens in practice. So we have a tiny matrix, 100 by 100. Condition number is 1000. Here's some eigenvalue distribution. And what we're going to plot is the pointwise error, which one doesn't have in practice, but we cooked up the problem so that we know the solution. So, and then the expected error, which is equal to the trace of the A times the posterior. And then you have 2 panels here, one in which we use the non-informative prior, and the other one where our prior is A inverse. So then we plot here the number of iterations going from 1 to 100, which is the dimension of our matrix. And then here we plot the error and the trace. So in black, we have the error. And in red, we have the error measure given by the covariance. So you see for both of them, it takes 100 iterations to converge. Well, we expected. However, unfortunately, what we see is that the error for the covariance is higher than the pointwise error. So that means the means of the posterior converge faster than the covariances. The covariances give us error estimates that are too pessimistic. And that's not that great, given that this is our purpose in life, right? Posterior covariance them out and we get things that are worse than we knew already. So that is the reasoning for the Krylov prior. This thing is impractical, but we'll still investigate it. And in order to concoct the Krylov prior, we need the maximal dimension of the Krylov space. So the Krylov space is as large as the dimension of the matrix, but depending on the right-hand side, the dimension of the Krylov space can be smaller. So for example, if R0 happened to be an eigenvector of A, then the Krylov space would just have dimension 1. So anyway, so the Krylov space dimension depends on this right-hand side. And let us denote by n the maximal dimension of the space, which we don't know in practice, but on paper we do. And then let's choose as the columns of this matrix V, the search directions from conjugate gradient, and let's normalize them to be A orthonormal. They then form a basis for this Krylov space. And then in the middle here, we have a matrix phi, which is a diagonal matrix. We declare it to be, I mean, this is we define things this way. And the diagonal elements are residual norms. And then these quantities gamma k, you don't really have to think about what they mean. But what matters is that these are the step sizes in the conjugate gradient algorithm. So that means these elements of the diagonal matrix are quantities we compute anyway in the conjugate gradient method. So they come for free. So we may as well use them. Okay, so what we do is this Krylov, so this is the Krylov prior. How about the posteriors? While we maintain the prior in factored form, we don't multiply out. We retain the V and we retain the diagonal matrix separately. And suppose we partitioned the basis and the diagonal matrix to distinguish the leading k columns here, the leading k diagonal elements here. And then suppose we multiplied out. then we can see that the prior is the leading k quantities plus the posterior at iteration k. So that means the posterior covariances are the trailing submatrices of our prior. So that is really nice because that means we don't have to do any computation for the posteriors. We just pick the trailing submatrices and there's our posterior. So, and these posterior covariances do capture the error of conjugate gradient. So the trace of the kth Krylov posterior, it's this, right? The trace is equal to, because if we put because of the commutative of the trace, so it's equal to the trace of the diagonal elements, and this is equal to the error in the conjugate gradient method. And this result is not ours. This is actually from the original paper by Hestenes and Stiefel in 1952. So it's always nice that whatever we are doing sort of has hooks or is connected to earlier work. And that's one way we hope of convincing numerical analysts that this makes sense, because many things we do agree with what people have done before in a deterministic setting. Okay, so here's a little local summary. So our probability distributions for BayesCG, if we had a general prior, so I'm contrasting the general prior to our Krylov prior. If we had a general prior, well, our means are iterates that approximate the solution, and the posterior covariances for variables that are distributed like the posterior covariances, these posterior covariances can reproduce the error in expectation. However, for the Krylov prior, we can say a lot more. We can say that our posterior means are identical to the conjugate gradient iterates. And our posterior covariances give the pointwise error, not just in expectation, but equal. So they give us the conjugate gradient error. And I feel like an infomercial, and you get this. And if you phone in the next 19 minutes, you get this too. And they require no computation. The downside, of course, is the whole thing is way too expensive. If we can compute the Krylov prior, we have solved the linear system. So it's sort of the hen and the egg problem. So what do we do now? While we try to find low rank approximations, right? That's what everybody does these days. If a problem is too expensive, we do a dimension reduction or low rank approximation. So here we come with the practical approximate Krylov posteriors. Krylov posteriors, those are the ones we approximate. So let's see what happens at iteration k of Bayesian conjugate gradient. We have a posterior covariance. It consists of quantities that we haven't computed yet. These quantities are from the future n-k iterations of the method that we haven't embarked on yet. And in particular, these are, so the diagonal matrix needs residuals and the V matrix needs search directions. So those are the quantities we don't have yet, n-k future quantities. While instead we'll say, well, let's shoot for less. Let's not work with n-k future quantities, but let's just work with L. And L can be small, 5 or 10. So that means we just have to do a small number of future iterations to construct an approximate covariance or an approximate posterior. And so we are thinking in terms of approximate posteriors. However, there is a corresponding prior, approximate prior that is sitting behind that, but we don't compute that and we don't think about it. Okay, so here is how you use it, how you run it. You have your matrix, you have your right-hand side vector, and then you have to decide how many more additional iterations of conjugate gradient are you willing to run to construct that prior. So that is L, script L. So then what do? You run conjugate gradient to convergence. What people have been doing, you take a code, you run until convergence, and you get your solution, your approximate solution, XM. Then you run L additional iterations. It's that L that you specified here. So you can think of that as, it's called delay in the literature, but it's sometimes easier to think about it as a look ahead. You look ahead L iterations. Those iterations give you search directions and residuals. From those, you construct the V matrix and the diagonal matrix. And the product of these is the approximate posterior. However, we don't factor, we don't multiply out, we keep them in factored form. So these L additional iterations that we are doing and the quantities we are computing there are the same quantities that are being computed when one does conjugate gradient error estimation with delay. So again, these quantities have been around. People know how to compute them accurately. What we do, however, is we use them to compute probability distributions, not just normalized error bounds. But again, it's nice that our new things are constructed from quantities that have been around for 20 years or more. Okay, so now you can ask, well, okay, so we have that approximate Krylov prior, but is it any good? And then, so we have to look at distances between probability distributions. The usual thing is to, do a Wasserstein distance. So here's the Wasserstein distance in the A norm, right? Because that's the norm induced by our matrix. Then we have our exact posterior. And then we have, which is this, and then we have the rank L posterior covariance. It's in here. And then the distance between the exact posterior and the low rank posterior in the Wasserstein distance is the difference between the two traces. So it's that easy. And the difference between the two traces is the amount by which our low rank posterior underestimates the true error. So that also makes sense. So whatever we ignored, that's the distance between the exact and the approximate distribution in the Wasserstein distance. So that makes a lot of sense too. So this difference in the Wasserstein distance is everything else we haven't used. Okay, so let's do some numerical experiments. So let's choose a matrix now with dimension a little bit larger, almost 12,000. Condition number 10 to the 6. We are going to do an incredibly large number of iterations between 1 and 2,500. Usually one doesn't do that many iterations. One does 10 or 20, but we want to see what's what. So we're going to do huge number of iterations. And then we are going to look at two Krylov posteriors. One has rank 1. That's the lowest, that's the most affordable posterior you can get, rank 1. And the other one has rank 50. And then we are going to show plots. We are going to show the error from the posterior means, which are also the iterates in conjugate gradient under our posteriors. And then the pointwise error from our approximate posteriors. And then in addition, errors from samples, because that's what we're really interested in. So we are taking our posterior and we are sampling from this posterior. And then we are looking at the difference between the samples and the mean. And we are plotting this. So this is going to be a surrogate for this error, because this error, we don't have it. So, but we are sampling in order to get a surrogate for this error. And it is this, if we propagate the mean and the covariance to other subsequent computations, they can do the same thing, they can sample from it. And that way will produce the error. So they're not just stuck with a normalized error bound, they can generate a lot of samples and probe how their computations react to these samples. And well, here's how you do it. It's very easy in MATLAB. So here you are seeing two plots. This plot is for the posterior of rank 1. This plot is for the posterior of rank 50. Here's the number of iterations from 1 to 2,500. Here is the error. So the pointwise error in black, and then the error from the trace, that's the pointwise error from the posterior covariance, and then in red are the samples. So if we are really cheapos and construct our posterior covariance as a rank 1 matrix, we'll see that our samples underestimate the error, because the true error is the black line here. And the trace from the covariance is underneath that black line. So we underestimate the error, and we knew that from the analysis. However, if we increase the rank of our covariance to 50, then in the eyeball norm, everybody looks the same. So that means, so in general, the posterior covariance gives us error measures that underestimate the error. And the samples from the posterior try to estimate the true error. And in our rank 50, our posterior covariance of rank 50, we basically, that rank is 0.5% of the matrix dimension. The matrix dimension is almost 12,000. We did 50 more iterations. That's really a drop in the bucket. And we got in the eyeball norm an error measure from these samples that is equal to, that's indistinguishable from the true error. And then one can, this case, we would take this rank 50 posterior, its mean and its covariance, and forward that to subsequent iteration. Okay, so here's the little local summary. So we have a solution of these symmetric positive definite systems with dimension D, and we chose a posterior whose rank is a small percentage of D. So we just do this many look ahead iterations L. And then we can compute these rank L posteriors, and it's the same amount of work as if we did conjugate gradient with delay or look ahead. So these computations are already there. And then if we compute posterior samples, of course, we need matrix vector products. And then the pointwise estimates that we get from our posterior covariance underestimate the true error. And this underestimate is equal to the distance between the approximate posterior and the true posterior. So this underestimate has a meaning, a physical meaning. And these errors here from the so we can sample random vectors from the posterior and measure their distance from the mean in the A norm squared. They represent accurate surrogates for the true error that we cannot compute. So that means we can take these approximate posteriors and ship them to subsequent computations. These computations then can sample and probe uncertainty in their computations with the samples from our posterior. So then the take-home message here is, this is the overall last slide. So our mission in life here was to solve symmetric positive definite systems. I was selling BayesCG, which is a probabilistic extension of the conjugate gradient method. And under this data-dependent Krylov prior, BayesCG reduces to the well-known conjugate gradient method that has been around for 70 years. Since we have probability distributions, we need priors. We decided to think instead of in terms of posteriors. So after we converged, we took a few more iterations to compute the posteriors. So they are cheap to compute, just a few more iterations and matrix vector products. They are numerically accurate because we maintain them in factored form. By doing that, we automatically ensure that those posteriors are positive, semi-definite, and symmetric. That's what the factored form assures us. And the sampling produces accurate surrogates of the error that we are interested in. And that we can take these posteriors and they give us the uncertainty we got from terminating conjugate gradient early because we couldn't afford to iterate till the very end. So we are working with people from Sandia on applying this to hyperdifferential sensitivity analysis in PDE constraint optimization. And for future work, while we have to increase the numerical stability and accuracy of the implementation, so to get a recurrence for the posteriors that was numerically stable in practice took us quite a while, and we still don't have a round of error analysis. We need to establish a rigorous and meaningful statistical setting because we are not doing true Bayesian inference because we are conditioning with the search directions, and the search directions depend on the solution. So there's a nonlinear dependence on the solution, and that is not a true Bayesian procedure. However, it sort of happens to work out. And then we need to implement efficient propagation of empirical uncertainty, because if one does it at several steps, it just mushrooms into a combinatorially many samples. Okay, thank you very much for your attention.
Excellent. Thanks a lot for the great talk. I will.
Exactly 50 minutes, right? Ha.
Yeah, yeah. I'll open up the floor to questions that anyone has.